Hi there and welcome to the next video in this series of stoichiometry we've been dealing with thus far. Now in this video we're going to be looking at something absolutely interesting. It's called relative atomic mass and relative molecular mass. Remember, this is the series for stoichiometry and we've had an awesome time thus far, and this is the topic we're going to be dealing with in today's video. So I want you to sit back, relax, and enjoy every bit of what I've got for you. Let's get into what we have on today's video. The relative atomic mass and the relative molecular mass are both interesting concepts to understand. And now that we already understand what the mole is, we treated the mole in our previous video. If you haven't, go back and watch it. This is a series, so the video before this one was talking about the mole. So now that we understand the mole, we need to understand or answer an important fact. Different atoms have different masses, just like different people have different masses. You cannot expect person A to be the same mass as person B. It is not possible because they are different. In the same way, to compare the masses of atoms and elements, chemists use something called the relative atomic mass. The symbol for representing the relative atomic mass is known as AR. In chemistry, when we write this, we're referring to the relative atomic mass. The relative atomic mass. And when atoms join together to form molecules or compounds, we use something known as the relative molecular mass. The symbol used to represent that is MR. I trust it makes sense at this point. If you're enjoying this, go ahead, like this video, subscribe if you haven't, and share to as many as you can so we can reach more students. Let's make some progress. So we begin by explaining the atomic mass simply. Now we said earlier on in this video that different atoms have different masses. For example, hydrogen, which is the first element on the periodic table with its symbol over here, happens to be a very light element. Another element, which is carbon, is way more heavier than hydrogen. And oxygen is another element that's heavier than carbon. And then finally, iron is much heavier than all of them. So you can see that as we progress from one atom, one element to another, the mass is changing. The mass is changing because the elements are also changing. Now, because of this, scientists assign numbers to represent these relative masses. These numbers are called the relative atomic masses. So if we are to define the concept of the atomic mass or the relative atomic mass, we would simply say they are numbers that are assigned to represent how heavy an atom is relative to another atom. I trust it makes sense at this point. Let's make some progress. So what is the relative atomic mass? The relative atomic mass is simply a number that tells us how heavy an atom is compared to a standard reference. Take note of this word relative. Relative means in reference to something, compared to something. So just think of it as the mass number that chemists use for an atom. These values can be found on the periodic table. When you check out the periodic table, you will find the symbol of an element. You would also find the atomic number of that element. And then one other thing you will find is the atomic mass of the elements. So you need to have all these things at the back of your mind. They are very, very important. Another question to answer now would be, how do we find the atomic mass or the relative atomic mass values? Well, most of the times these values are given in examinations, but if they are not, they can be found on the periodic table. For instance, the relative atomic mass of hydrogen is 1. That of carbon is 12. That of oxygen is 16, and that of nitrogen is 14. And finally, magnesium is 24. These are all examples of some elements that are found on the periodic table and the atomic masses. So now that we have talked about the atomic mass, let's move on to the other concept, which is the relative molecular mass. Well, you know that an atom is a single unit, while a molecule is produced when more than one atom joins together. More than one atom joins together. So when more than one atom come together to form a molecule, things become more interesting. Remember, a molecule contains more than one atom. For instance, we have H₂O. This stands for water, and it's a molecule because it contains more than one atom. We have CO2, which stands for carbon dioxide. Carbon dioxide, and it contains more than one atom, so it's also a molecule. We have NH3, which is ammonia, and it's also a molecule because it contains more than one atom. And finally, we have CH4, which is methane. All these guys are called molecules because they contain more than one atom. So when things like this happen, how do we get the relative molecular mass? To get the relative molecular mass, we simply add together all the relative atomic mass values of the atoms present. That answer that we get from this is called the relative molecular mass. So in simple English, add everything together. That's what we're trying to say. I trust you're getting value for what's happening in this video. Let's check out some examples and see if we can make some progress. We have the first molecule, which is water, H₂O. So we are asked to find the relative molecular mass, Mr, of water. Step number 1. Write the elements. So how many elements can be found in water? We have hydrogen, H, and we have oxygen, O. Step number 2. Write the number of units present. For hydrogen H, we have 2 units present. As you can see in H₂O, H₂O. This 2 here stands with hydrogen. So hydrogen has 2 atoms. So because it has 2 atoms, it now becomes 2 multiplied by the atomic mass of hydrogen. And the atomic mass of hydrogen is 1. So we have 2 times 1, that gives us 2. And then for oxygen, oxygen appears just once. You can see over here oxygen appearing once. 1 times the atomic mass of oxygen, which is 16. That gives us 16. Step number 3 would be to add everything together. Add everything together. So we have 2 plus 16. That gives us 18 grams per mole. This is the unit for measuring the relative molecular mass, 18 grams per mole. That is for water. I trust you understood that. Let's take yet another example. We have ammonia on the screen, NH3. So step number 1, write out the elements. We have N, which stands for nitrogen, and we have H, which stands for hydrogen. Now the next thing to do would be to write the number of times they appear. Nitrogen N appears just once, and hydrogen appears 3 times. You can see in the molecule NH3. This 3 belongs to hydrogen. Now the next thing to do would be to multiply each one by the atomic mass. N has the atomic mass of 14, so we have 1 times 14. This gives us 14, and then we have 3 times the atomic mass of hydrogen, which is 1. This gives us 1. And then finally we add everything together. This becomes, I beg your pardon, 3 times 1 is not 1, 3 times 1 is 3. So we have 14 plus 3. This gives us 17 grams per mole. This is the relative molecular mass of ammonia. I trust you're getting massive value for what's being put out in today's video. The next example on the screen says calculate the relative molecular mass of sodium chloride. Well, step number 1, let's write out the elements. We have sodium Na and we have chlorine Cl. Step number 2 will be to write the number of times that they appear. Sodium appears just once, chlorine appears just once as well. Now the next thing would be to multiply each one by the relative atomic mass. Sodium becomes 1 times, the relative atomic mass of sodium is 23. 1 times 23 gives us 23. And then we have for chlorine 1 times, the relative atomic mass of chlorine is 35.5. This gives us 35.5. The final step would be to add everything together. So we have 35.5 plus 23. This gives us 0.5. This gives us 8, and this gives us 58.5 grams per mole. Easy peasy and straight to the point. I trust you're getting the hang of everything we're putting out. And then we have this other example on the screen, magnesium oxide. Well, let's take step number 1. We write out the names of the elements. We have magnesium, Mg, and we have oxygen, O. Next thing to do would be to write the number of times they appear. They appear once for each element. Magnesium appears once, oxygen appears once as well. The next thing to do would be to multiply each one by the atomic mass. Magnesium has an atomic mass of 24, so this becomes 1 times 24, and that's equal to 24. And we have oxygen to be 1 times 16, because the relative atomic mass of oxygen is 16. This becomes 16. So altogether, we have 24 plus 16. This gives us 40 grams per mole. That's the answer for magnesium oxide. I trust you're getting massive value for this. And then we have another interesting compound on the screen, calcium hydroxide. Now I want you to pay attention at this point. You can see that there are a pair of parentheses, brackets over here. So how do we handle molecules that have that? Well, that's why I'm here. Let's take it step by step. Step number 1, we write the elements that are present. We have calcium, we have oxygen, and we have hydrogen. You can see oxygen over here, you can see hydrogen over here. The next thing to do would be to write the number of times they appear. Calcium appears just once. Oxygen over here is in a bracket, and that bracket has a number standing outside it. That number is 2. What this means is that everything inside this bracket is affected by this number 2. So it means that whatever is in the bracket will be multiplied by 2. So you can see oxygen over here, and it's affected by the 2 standing outside. So it simply means that oxygen appears 2 times. The same thing goes for hydrogen. Hydrogen also appears 2 times. That's the essence of number 2 standing outside the bracket. So the next thing to do now would be to multiply each one by the atomic mass. For calcium, we have 40, so this becomes 1 times 40. This is equal to 40. For oxygen, we have 2 times 16, this is 32. And hydrogen, we have 2 times 1, this is 2. So altogether, we have 40 plus 32 plus 2. This is 4, and this is 7. 74 grams per mole for calcium hydroxide. Can you see how easy it is to do all of this when all these concepts are put in place? So one more example, we have calcium carbonate, calcium trioxocarbonate on the screen. So let's write out the elements. We have calcium, Ca, we have carbon, C, and we have oxygen, O. How many times does each of them appear? Calcium appears just once, carbon appears just once as well, and oxygen appears thrice or 3 times. You can see the subscript of 3 standing right beside oxygen. The next thing to do would be to multiply each one by the atomic mass. Calcium becomes 1 times 40, which is 40. Carbon becomes 1 times 12, which is 12. And oxygen becomes 3 times 16. This is 48. Yes, 48. So altogether we have 48 plus 40 plus 12. This is 8 plus 2, that gives us 10, 0 carry 1, 4 plus 4, 8, plus 1, 9 plus 1, 10. So we have 100 grams per mole. That's the answer for calcium trioxocarbonate. Did you see how all of these things are being done? And then we have another example. I'm giving you plenty of examples so you can get the hang of how these things are carried out. So we have CH for methane on the screen. So we write the elements C and H. C, carbon appears once, H, hydrogen appears 4 times. So for carbon, we have 1 times 12, and hydrogen, we have 4 times 1. This is 12, and this is 4. Altogether, we have 12 plus 4. This is 16 grams per mole for methane. Pretty straightforward. And then we have for sulfuric acid, H₂SO₄. So let's write out the elements. We have H, hydrogen, S, sulfur, and O, oxygen. For hydrogen, the number of times it appears is 2 times. You can see the subscript over here. Sulfur appears just once, and oxygen appears 4 times. For hydrogen, it becomes 2 times 1 because the atomic mass of hydrogen is 1. Sulfur becomes 1 times 32, and oxygen becomes 4 times 16. So altogether, we have this is equal to 2, this is equal to 32, and this is equal to 64. So altogether, we have 64 plus 32 plus 2. This gives us 8, and this gives us 98 grams per mole for sulfuric acid, H₂SO₄. So the summary of all we've been saying since the commencement of this video is AR refers to the relative atomic mass, and AR tells us the mass of an atom. Different elements have different atomic masses, and MR means the relative molecular mass, and you've seen how to calculate that. And it is also found by adding all the individual atomic masses present in a molecule. Always count atoms carefully before calculating. You saw how we calculated and indicated the number of times each atom appeared. That's very important. So most of the molecular mass calculations are simply careful addition. That's the summary of all we've been saying since the commencement of this video. So here are some practice questions I'd like you to try out before we move on to the next topic. We have calculate the molecular mass of hydrogen, the hydrogen molecule, oxygen molecule, nitrogen molecule, chlorine molecule. Here are their atomic masses for hydrogen, oxygen, nitrogen, and chlorine. Go ahead and do that. Here are another set of questions. You can pause the video and write down the values if you want. Here are some more molecules for you to calculate the values of. Go ahead and do that. Drop your answers in the comment section, and I'll be at the other side to respond. Here are some more molecules for you to calculate the molecular masses for. It's been an interesting series thus far. Here are some more I'd like you to calculate. You can pause the video and write them out. Some more for you to do. Pause the video and write them out. A compound contains 2 carbon atoms, 6 hydrogen atoms, 1 oxygen atom. Calculate its relative molecular mass. Calculate its relative molecular mass. And then we have another question on the screen. Which one has the greater molecular mass? Is it water, H₂O, or CO₂? Show your calculations, and I'll be at the other side to answer your questions and answer your comments as well. A student calculated the mass of CO₂ as 28. Explain the mistake and determine the correct answer. So at this point, you now understand what a mole is, what the relative atomic mass is, what the relative molecular mass is. Now you are ready for the next step. And that next step, my friends, is the mole formula. I'm looking forward to seeing you in the next video. I trust you enjoyed every bit of what we did in this one. Up until then, my name is David, and I'm an online chemistry tutor for high school kids. I'll see you in the next one.